Hello, welcome to another practice problem. This one we're going to work on 11.59 out of the text. It says here, a timber beam is loaded and supported as shown. The cross-section of the timber beam is 4 inches wide and 8 inches deep. The beam is supported at B by a 1/2 inch diameter steel rod, which has no load before the distributive load. 900 pounds per foot is applied to the beam. Determine the force carried by the steel rod, the maximum bending stress on the timber beam, and the deflection of the beam at point B. And point B is halfway. It's at the midpoint. So the first thing that I kind of want to do is let's just jump into what we know and what we've done in the past is let's solve for the moment of inertia of our beam, which is base times height cubed over 12, right? So the moment of inertia is then going to be, our base is 4 inches by our diagram here, so 4 multiplied to 8 cubed divided by 12. And then this will, rounding, we'll say 170.67 inches to the fourth, okay? And we're also asked to find the maximum bending stress in the timber beam and then the force in the steel rod. Something that might be useful is let's just go ahead and solve for it now. The cross-sectional area of the steel rod. So the area is going to equal pi over 4 diameter squared. So the area of the rod, right, is pi over 4 multiplied to 1/2, so 0.5 squared, and then this equals 0.196395 inches squared. Okay. So now that that's out of the way, let's draw really quick just of our loading here. We have a beam, okay, and our beam that's drawn here, we have a couple of reactions at point A. So AY, we have a reaction, and CY is a reaction. There is a point load directly in the center, right? Because the steel rod is, we have a distributive load working on this timber beam, pushing it down. That steel rod we can model is a point load going up, okay? And we'll just call this F sub 1. And then we have a distributive load that works all the way across at 900 pounds per foot, right? So this is what we have. So in chapter 11.5, we're going to use a superposition method, and I believe in the class you're given a handout. In that handout, what we can do, or even in the back of the book in the appendix, we can find a couple of formulas, because we have two cases here. We have a case if we analyze our simply supported beam with just a point load in the center, and then another simply supported beam with a distributive load. So what we can do, let's go ahead and pick the distributive load first and say we have, I'll just draw both of them here. So here's distributive load. With and then a point load on this one. So two separate cases, right? And we can analyze each one of these based off of the formulas in the textbook, okay? And the formulas given, we can look for the maximum. We'll just use deflections, so the maximum deflections, and say for our distributive load, we'll say our deflection max is going to equal, based off of the formula in the book, 5QL to the fourth divided by 384 EI. Okay, and this is for the distributive load. And for the point load, delta max is going to equal PL cubed divided by 48 EI. And these are, again, just to reiterate, the formulas in the appendix in the back of the book or the handout that you received in class. And so on this formula here for the distributive load, Q is in reference towards, we could say Q equals the 900 pounds per foot, okay? And then the length is going to be the entire length, right? So in this case, it's 14 feet. Okay. So for our distributive load, to find the maximum deflection, which is going to be in the center, which also corresponds to point B, right? We'll just go ahead and plug all our values in, and it's I'm sorry, this was a negative. I did it wrong. So negative 5 multiplied to 900 pounds per foot multiplied to 14 feet to the fourth, right? And then we have a unit conversion that we need to do. So pounds per foot is going to take care of one of these, right? Because we have foot to the fourth, which means there's a foot cubed left. So we'll go ahead and do a conversion and multiply this to 12 inches per foot cubed divided by, and this will put everything in inches, so our modulus of elasticity and our moment of inertia will all be compatible. So our modulus of elasticity for the wood, we're going to use, this is kips per square inch, so 18 KSI, kips per square inch, and so we have 18 kips per inch squared, right? And then multiply that to, we'll say 1,000 pounds per 1 kip, and then multiply this to our moment of inertia that we found up here, which is 170.67 inches to the fourth. 170.67 inches to the fourth. Okay, and run through our units real quick. So we have pounds up here divided by feet, and then this to the fourth, so one of them is canceled here. This will take care of it and leave it into inches, so will be inches cubed on top. And then we have a kip divided by a kip, that leaves us with pounds over square inches, and square inches, or inches to the fourth divided by inches squared leaves us inches squared, and then we'll be left with our max deflection here in units. So all the units check out. Max deflection due to the distributive load is then going to equal negative 2.532305 inches. Okay? And so now let's do the same thing that we did with the distributive load with the point load. Okay? Now, something to note with the point load, due to the force in going in the opposite direction than what's actually shown in the handout or what's in the appendix of the textbook. In the appendix of the textbook, the force is going down, right? So to be able to account for that, and it also calls it P in our formula, so we can say that P equals negative F1, right? And so our deflection max then equals negative F sub 1 L cubed over 48 modulus of elasticity multiplied to moment of inertia. So we don't know what F sub 1 is. In fact, that's actually part of the problem. In section or part A, we need to find out what that force is. So the first thing that we do is we'll just go ahead and say our deflection max. We'll just, and this will be due to the point load. Deflection max will be, and we'll plug all of our values in. We get negative F sub 1 multiplied to the length, which is 14 feet cubed. And do a unit conversion, so this will be 12 inches per foot cubed divided by our 48, and then we'll have 18 kips per inches squared multiplied to 1,000 pounds per kip multiplied to 170.67 inches to the fourth. And so deflection max due to the point load is going to be 321.5625 times 10 to the negative sixth, and this is inches per pound, right? Because we don't know our force yet, and are multiplied to our F value, okay? F sub 1. So this deflection, what we can do is we're kind of, how do we solve now for F sub 1? So what do? Well, we have another relationship that we can use, going back to why at the very beginning of the problem I solved for the area of the steel rod. Well, using this area, going back a couple of chapters, what we can do is determine the deflection of a member is going to equal the force multiplied to the length divided by the area and the modulus of elasticity. So we'll say 1 here because this is due to the deflection of the steel rod, okay? And modulus of elasticity is going to be 30 kips per square inch. So deflection of the rod is then going to equal our force, F sub 1, multiplied to the length of the rod, which if you look at our diagram here, length of the rod is 16 feet. Okay, so 16 feet, and do a unit conversion, 12 inches per foot, divided by the area, which we've already determined is 0.196395 inches squared, multiplied to the modulus of elasticity is 30 kips per square inch, but I'll just make it 30 times 10 to the 6 pounds per square inch. And so now we get a deflection of the steel rod in terms of F, again, is going to be 32.59493 times 10 to the negative 6 inches per pound multiplied to F sub 1. Okay? So, and one note about this little relationship that we've established here, this is deflection of the steel rod, but if you look back at the diagram here, if this steel rod deflects, right, if this goes down, right, this deflection down is going to be the same deflection as this, right? So, and that's part of the point, or part of the problem statement. So part C asks to find the deflection at point B. Well, the deflection at point B is the same as the deflection of the steel rod. So we can say deflection at point B equals the deflection of the steel rod, which equals, we can just say negative 59493 times 10 to the negative 6 inches per pound multiplied to F sub 1. So when we find F sub 1, we can also immediately just plug F sub 1 into this and then solve for part C. Okay? So the next step, we can just go ahead and relate all of our deflections. Okay? Using our superposition method here, we can state that the deflection maximum from the distributive load, right, plus the deflection maximum of the point load is going to equal the deflection that we just solved for here. Okay, so putting these together, we get negative 2.539 0.2305 inches plus 321.5625 times 10 to the negative 6 inches per pound multiplied to f sub 1 equals negative 32.59493 times 10 to the negative 6 inches per pounds multiplied to f sub 1. Okay? So also this should be conceptually, pay attention to the signs. So the deflection due to the distributive load is negative. Deflection due to the steel rod is also negative because they're both going down. And then deflection due to the point load, we're accounting that as a positive because it's going up. Okay? So solving for f sub 1, you can do your algebra. F sub 1 should equal 7,150.22 pounds. And this is in tension. Okay? So that's part A. So we can box this off. Part A, solved. So part C, so I'm just going to skip B real quick. We'll come back to it. But I'm going to jump up to part C because we have this already, right? So part C, I can now solve for the deflection at B, which we already determined is this equation up here, right? Once I know F1, I can just plug it in and solve for it. So negative 32.59493 times 10 to the negative 6 inches per pound, and multiply this to 7,150.22 pounds. And our deflection at B then should equal 0.233 inches. And it's a negative, right? But we can just say that deflection at B equals 0.233 inches going down. And then this is the answer for part C. Done. Okay? So now part B. What was part B again? B said the maximum bending stress in the timber beam. So what is maximum bending stress, right? Zoom in here. Maximum bending stress, right? So sigma sub B equals my over I, right? Well, to be able to find what our maximum bending stress is, we need a moment equation, or a moment, right, at point B. So to be able to solve that, let's just go back to what we learned in statics. We're going to draw our shear and moment diagrams. That's our shear, and this is moment. Okay, and so shear, which will be in pounds, and moment, which will be pound-feet. And so our shear, solving for our reactions, which you could do through statics, because now you know your forces, right? You can just draw a free body diagram of this section here, this assembly, and then solve for your exterior reactions, and you should be able to solve it at A. We go up, come down at B. We'll have a jump, a jump at B, and then go down again like this. So the shear diagram should look like this, and the values should be 2,725 pounds, and negative 3,575 pounds, 3,575 pounds, and then a negative, because it's symmetric, it'll be the same, so 2,725 pounds here. Okay. And if you wanted to, you could find the distance length here too. Okay, or this should be x. So moment equation. It's going to be maximum at all the points where it crosses 0, right? So at all these points where the shear diagram crossed 0, that's our maximum of the moment. And so since this is positive over here, find the area under the curve of the shear diagram, and you should find that height, and then since it's crossing 0 here, we'll have a negative 0. So this will go down, right? Or a negative maximum, sorry, not 0. And then it goes up again. So we'll have another positive maximum, and then it goes down. And again, it's symmetric, which my drawing doesn't quite look symmetric, but just use your imagination. So here's a negative moment, which will be negative 2,976, and the positive moment here will be 4,125, which is the same as here, 4,125. Okay? So now that I know my moments, right, what's our deflection at point B? Or I'm sorry, the maximum bending stress. Maximum bending stress is sigma. That looks terrible. Sigma equals the moment multiplied to y divided by I, and our maximum moment occurs at these points, and so m equals 4,125 pound, but what were my units here? Pound feet, right? So let's go ahead and multiply this by 12. 12 inches per foot, and just to get the units to match, and so 49,500 pound inches is my moment. Okay, so since we have a rectangular beam, right, I'm going to zoom in on this. At what point, if my beam, if we say this is the neutral axis, right? Neutral axis, which is 4 inches, right, from the edge, right, to get to the centroid. It's just taking 8 divided by 4. We know that if I was to draw a bending moment diagram off of here, we'll have a diagram that looks like this, right? And the max, so this is going to be our maximum values, and it's going to be 0 there at the neutral axis, right? So that means the y value is going to be from the neutral axis to the outermost edge, which is going to be 4 inches, okay? So going back to our equation, we can say sigma bending max is going to equal 49,500 pound inches multiplied to 4 inches divided by the moment of inertia that we solved for earlier. And so once you do this, you should find that your stress maximum is going to equal 1,160 pounds per inches squared, or 1,160 psi. And this is the answer to part B, okay? And that's it.